All right, so let's go. Today we're going to finish up our discussion of crystal field theory. We said that we're going to tack on this extra theory to our VSEPR theory that's going to help us explain these new covalent compounds, these transition metal complexes, because they don't behave like regular covalent compounds. All right, so we have this crystal field theory that helps us explain those differences. In particular, it explains the magnetic properties of these complexes. That's what we discussed last class, how to build those electron configuration diagrams and determine whether your complex is going to be paramagnetic or diamagnetic. And the other thing that it helps us to explain is the color of those complexes. Right? Our transition metal complexes, they can be very brightly colored. All right, so that's where we need to pick up with here. The color of our complexes. All right, again, these transition metal complexes have pretty colors. All right, so before we can kind of scratch the surface of why our transition metal complexes have color, we first have to address the elephant in the room here, which is what the heck is color? All right, so importantly, why we can see period is because of these photons that we have shining down on us from the light bulbs in the ceiling, okay? The light emits this particle called a photon, and it comes and bounces off of me and then into your eyeballs, and that's how your eyeballs are able to detect my presence here, because they're registering those photons that are bouncing off of me, okay? What we call white light, what's being emitted from the light bulbs above, is a mixture of all the photons that make up the visible region of that electromagnetic spectrum. All right, so importantly, white light is a mix of all photons in what we call the visible region. Of the electromagnetic spectrum. Basically just the spectrum of all possible photons that could exist. There's a certain region we call the visible region. These are the ones that our eyeballs can detect. And these are when that photon has a wavelength between 400 nanometers and 800 nanometers. All right, we use this fancy symbol here for wavelength. It's this little, I don't even know, it's got a little hat on it. It's a lambda, actually. It's a lambda, yes. But it is a letter of the Greek alphabet. Yeah, gamma's upside down. Okay, so basically when this white light's coming down from the light bulbs, it's a mixture of all different photons that have a wavelength ranging from 400 to 800 nanometers. All right, so it's a mix of all of them that we can see. Okay, cool. So then where's the color coming from here, right? So why is my shirt red? It's because when this white light comes down from the ceiling here, it bounces off of my shirt, but my shirt absorbs some of those photons. all right? Because it's absorbing some of those photons, what's making its way to your eyeball is no longer that white light mixture of everything. It's got some stuff missing because my shirt absorbed it, all right? So our eyeballs are just super fancy photon detectors. If we see all photons within this range here, if we got a mixture of everything, we perceive that to be white. If it has a color associated with it, it's because it's absorbing a few of those photons. All right, in the case of my shirt here, it's probably absorbing a photon around 500 nanometers. What's making it to your eyeball is missing that wavelength, and your brain processes that as a color, as red. All right, so that's where our color is coming from here. Okay, so something appears to have color. When it absorbs a photon from the visible spectrum. All right, so how did I know that it was 500? We're going to work up to that. All right, we're going to have a tool to tell if something absorbs a specific color, absorbs a specific wavelength, what's its color going to be. All right, so we've sort of seen this before when we were looking at those iron thiocyanate compounds. We took advantage of the fact that they absorbed light to measure their concentration using those spectrophotometers. All right, so we have our light bulb here. And it's going to shine into this sample. Remember, we used those little plastic things we call cuvettes. All right, well, if this light bulb, again, is shining in white light, that means it's a mixture of a bunch of different wavelengths. All right, ranging from 400 nanometers, we'll say this one's 500 nanometers, 600 nanometers, et cetera, et cetera. All right, and what happens is that sample absorbs, pulls out specific photons. All right, in this case, my 500 nanometer wavelength was absorbed. Right, so the instrument did some fancy calculation here, but if we were just using our detectors, our eyeballs, what we would see is this red color. Cool. All right, so something appears to have color to it if photons are being absorbed by that sample. That's what our eyeball perceives. Those missing wavelengths are what our eyeball perceives to be color. All right, so then the next question would be, all right, well then why do these compounds absorb photons? All right, so our photons are being used. These photons will excite electrons from lower energy levels to higher energy levels. All right, so what the heck do I mean by that here? All right, so when my shirt is absorbing those 500 nanometer wavelengths, it's because the photons are being absorbed by the dye molecules in this shirt. And why are they being absorbed by those dye molecules? Because the electrons in those dye molecules are being excited. They're being kicked from a lower energy level to a higher energy level. All right, so we've kind of been looking at these orbitals for a while. So let's draw a little diagram here of what we're talking about. So we have these energy levels and we have these orbitals here. All right, and in this lower one, we're going to put a pair of electrons in there. All right, so this lower energy level you can see has a pair of electrons in it. The other one is empty, just an empty orbital. We call this one here the HOMO. They really thought this one through. The highest occupied molecular orbital. All right, and the empty one above it we call the LUMO. The lowest unoccupied molecular orbital. All right, and what this we're going to send a photon in here. All right, I'm going to use this little squiggly line to represent this photon that's being shown on my sample here. And what's going to happen is that photon's going to get absorbed by this molecule here, promoting an electron from this lower energy level, from the HOMO, to the higher energy level, to the LUMO. All right, so in our diagram here, if we were to show that photon is absorbed, all right, what that's going to do is take this electron from down here, from this lower energy level, and kick it up to this higher energy level. All right, we're going to excite this photon. It's all very exciting. All right. And that is why a photon is being absorbed. The energy of that photon is being used to kick that electron from a lower energy level to a higher energy level. All right. And with this process, will just kind of repeat itself over and over and over again. because once this electron is excited, it quickly relaxes back down to its original position. Right? So a dye molecule is not just able to absorb one photon, but many photons back to back to back, because it's exciting these electrons, but then they're relaxing back down again. All right? This relaxation is usually just emitting heat. And we're talking about a teeny tiny quantity of heat. All right, but most of that energy just gets converted into thermal energy. There is a special process where sometimes it's actually a photon that molecule emits. A process called fluorescence. If you've ever seen something glow under a black light, that's like an especially cool example of fluorescence, because you're exciting it with this UV light that your eyeball can't see, and then it's emitting this visible light that you can see because it's one of those special fluorescent compounds.
Is the light emitted always lower energy than the light?
Yes. Yep.
Never the same?
No. No, there's always some sort of like relaxation that takes place. Sometimes they're pretty close. Anyways, yes, we take advantage of this quite often. You'll talk a lot about fluorescence as like an experimental technique in sort of more advanced chemistry courses. All right, but importantly, so we established that color comes from the absorption of photons. Why do things absorb photons? Because they kick electrons from lower energy levels up into higher energy levels. Cool. All right. So then the last question is then why do our transition metal complexes have color? All right, well, remember what we learned how to do last class when we were discussing the magnetic properties of these compounds. We couldn't just look at their normal old, all by themselves, all left alone electron configurations. We had to pay attention to this crystal field splitting. The fact that our d orbitals have split up into two different energy levels. All right, so then why do our transition metals complexes have color? Because of that crystal field splitting. All right, this creates two different energy levels. For our electrons to transition between. All right, so if we took our transition metal complex here, and this thing, we shone a photon into here such that it absorbs a photon. Well, just as we showed before, we're going to excite an electron from a lower energy level to a higher energy level. All right, an electron gets kicked from this lower energy level to a higher energy level. All right, so those same crystal field splitting diagrams that we saw before, we needed to use them and to fill them in with these electrons here to help explain the magnetic properties of these complexes. Just the fact that there is this gap that exists in this diagram is the reason why these transition metal complexes have color in the first place. They can absorb electrons, promoting them from a lower energy level to a higher energy level. Cool. All right, so let's take a look at this thing here. This is this tool on our constants page, this color wheel, and we need to know how to use it. All right, so let's start off. I'm just going to tell you that the titanium, or rather the hexa aqua titanium 4 complex, absorbs 500 nanometer photons. All right, what is the color? Specifically, what is the color that we observe? All right, so what we got to do is we got to find our 500 nanometers on our spectrum here. All right, so here's about the 500 nanometer mark. Okay, and this is what's absorbed. All right, so importantly, if we had a flashlight and that flashlight had a light bulb in it that only shone 500 nanometer wavelength, then that would appear to our eyes to be green here, right? If I was shining 500 nanometer light at you, kind of greenish blue, right, sitting in the middle there. So if something emits (500 nanometer), then we would observe green. Kind of greenish blue, but since this wheel's kind of cut up into these blocks here, we'll be really definitive about it. But that would be if something emitted that 500 nanometer light. All right, if something absorbs, which is what our complex is doing, 500 nanometer photons, then we observe its complement, meaning what's on the exact opposite side of our wheel. So this complex here would appear red, kind of reddish orange sitting in the middle there. But this one, we would observe the complement of green, which is red. All right, so it absorbs on one side of the wheel. What we observe is, again, what we call the complement, meaning it's on the opposite side of the wheel. All right, so just real quick, if we said that something absorbed instead at 450 nanometers, what would we observe? Yeah, so we want to find on our line here 450. We go to the opposite side for what we observe. Okay, cool. Cool. All right, so what is the color observed? Our complex would be red here if it absorbs at 500 nanometers. Cool. All right, we're going to go. We got one more use for this wheel here, but we're going to introduce the next thing, which is how we talk about this stuff quantitatively. All right. So first of all, we said that if our transition metal complex absorbed a photon, it would excite an electron from that lower energy level to our higher energy level. Okay? Remember, we had a name for this difference in energy here. We used this uppercase delta. That uppercase delta, that's our crystal field splitting energy. All right, well, in order for this photon to be absorbed by this complex, all right, first of all, note when we're talking about color, we're not talking about absorbing like all the photons. It's kind of picking select ones out, right? So in order to absorb a photon, the energy that's imparted on that electron has to exactly match that gap in energy that you're giving to your electron. If you're promoting your electron from this energy level to this energy level right here, that means the energy of that photon has to be exactly equal to that distance, right? So our crystal field splitting energy is going to be exactly equal to the energy of the photon absorbed. All right, and this gives us a neat way that we can use to measure what that difference in energy is. All right, so we're going to learn how to calculate that crystal field splitting energy. All right, so the basis here is, again, that it's going to be equal to the energy of the photon absorbed. Well, fortunately for us, Einstein, pretty early on, established this relationship between the energy of a photon. All right, this is equal to hc over lambda. H and C are both just constants. H is what's known as Planck's constant, and C is what's known as the speed of light in a vacuum. And lambda we've seen before. What's our lambda? The wavelength. All right, and since H and C are both constants, the only thing that can vary here is that wavelength. All right, so the energy of a photon is inversely proportional to its wavelength. And that's great because we can measure the amount of our photons that are being detected. Right? Just like we said when we used our spectrophotometer here, we use this to illustrate how we would see red. Well, if we got instead of our eyeball some sort of a fancy detector, it can tell us exactly what's being absorbed from that sample. All right, so this detector here would allow me to say, all right, we're missing this 500 nanometer photon, so I know that my complex here absorbs at 500 nanometers. All right, so since we can use this spectrophotometer to measure the wavelength being absorbed, we can then calculate the energy of the photon, since that depends on our wavelength. And again, this is exactly equal to that crystal field splitting energy in our complex. All right, we can note H takes on a value 6.6262 times 10 to the negative 34. Teeny tiny number. Actually, hold up. Let me double check. It's 34 or 36. 34. All right, wonderful. What are you doing here? All right, and our speed of light we're going to use from our constants page here, 2.9979 times 10 to the 8. Yeah, so let's note our units as well. Our units for H are joules seconds. And our speed of light here, that 2.9979, question mark, 79. Is in meters per second. So exactly, if we were to calculate this here, plugging in our values, and we plug in our wavelength that we know here, those 500 nanometers, indeed we have ourselves a unit problem. If we're going to be calculating the energy of this photon, what units do we want at the end? Joules. So our seconds will cancel out, but we need to get rid of these nanometer and meters. So we're going to have to go back to our constants page and note a nanometer is 10 to the negative 9 meters. All right, so 1 nanometer is 10 to the negative 9 meters. Now my units will work out nicely, and I'll be left with just joules. All right, so if we punch this into our calculator, we get 3.97209 times 10 to the negative 19 joules. Is that a big number or a little number? It's a super tiny number, right? Why is that so friggin' tiny? Because it is literally the energy of just a single photon. All right, so what we just calculated here is joule of a single photon with lambda equal to 500 nanometers. All right, well, when we report our crystal field splitting energy, we're going to do so in terms of kilojoules per mole of our complex. All right, so we're going to take this value here, our energy of our photon, and we're going to do a little bit more work to it. All right, our crystal field splitting energy here is going to be equal to that 3.9729. That's how many joules are in one photon. All right. How are we going to get that into moles? Well, we know that by our Avogadro's number, there are 6.0221 times 10 to the 23 photons in 1 mole of photons. All right, and 1 mole of photons would be absorbed by 1 mole of complex. All right, and then lastly, just for making the number pretty, we're going to put that into kilojoules per mole complex instead of joules, so I'm going to divide by 1,000. All right, so we're going to take our energy of our photon and multiply it by Avogadro's number, divided by 1,000. All right, and so the crystal field splitting energy would be 239 kilojoules per mole. All right, so again, that spectrophotometry gives us a way to measure that crystal field splitting energy. Cool. All right, and this is all based on this very important principle up here, right? The whole reason that this works is because that gap in energy that electron jumps, our crystal field splitting energy, is exactly equal to the energy of the photon being absorbed. That's the rule. In order to absorb the photon, it has to use exactly that much energy in that excitation. Cool. All right, so then with that in mind, there's one more thing that we can do, one more thing that I can ask you, and it actually goes back to color here. All right, I told you that this hexa aqua titanium 4 complex absorbed at 500 nanometers. And we established that that meant that it would appear red to our eyeballs. All right? So the next question that I could ask is, what are the possible colors of the titanium, or rather hexacyano-titaniate or whatever. I don't even know what that one is. It's not on our naming list. Doesn't matter. This complex here, where I take this titanium, same exact oxidation number, same geometry, but I outfit it with these 4 cyanide ion ligands. All right, what are the possible colors of this complex? All right, so how are we going to figure this one out? Again, we know our water complex here absorbs at 500 nanometers, but now we got a new complex with a new ligand. All right, what's going to happen when we swap out that water ligand for this cyano ligand here? All right, well, let's remember we have this spectrochemical series, right? What is this series telling us here? What is this ranking? This is ranking these ligands from the smallest crystal field energy, crystal field splitting energy, to the largest. right? Well, so when I make my complex with my water, I get this very small gap in energy between those two energy levels. When I make it with my cyano complex, now I got a very large gap in energy between those two energy levels. All right, so is the energy of the photon absorbed by these two complexes going to be the same? No, because we got a different crystal field splitting energy here. All right, not only that, because of our spectrochemical series here, we know that the cyanide ion is going to have a larger crystal field splitting energy than water. So how is that going to correspond to the wavelength of the photon absorbed? All right, so let's go back to Einstein's equation here. All right, H and C are constants. They're not going to change here. So really we're looking at the relationship between this variable and this variable here. Right? And what we want to note is that they are inversely proportional. All right, so what does that mean? Well, if I have a large energy for my photon, what does that mean about its wavelength? Is it going to be big or little? It's going to have to be a small lambda. Likewise, a small energy implies a large lambda. Right? These are inversely proportional with one another. I know that my water complex has a smaller crystal field splitting energy than my cyano complex. That's what my spectrochemical series is telling me. It's telling me that that gap in energy is smaller for my water complex, this thing here, this gap, and it's larger for my cyano complex. And again, since this is inversely proportional to our lambda here, since this one's the small delta, that means it's going to absorb at the larger wavelength. Since this one's the large delta, it means that it will absorb at the smaller wavelength. All right, so there's no way that we can say for sure here what the color of this complex is going to be. What we know is that it has to absorb less than 500 nanometers. Somewhere in this region here, that cyano complex will absorb because it's less than that 500 nanometers. All right, so maybe it's just a little bit less and it still absorbs in that green region, meaning we see red. All right, maybe it absorbs even lower, between 490 and 430, where we would perceive it to be orange. Or maybe it is even lower than that, to where we perceive it to be yellow. All right, so we're going to say most likely going to be red, orange, or yellow. All right, again, because of our spectrochemical series here, we know the difference in energy between those two energy levels in our aqua complex is less than our cyano complex. That means that our wavelength for our aqua complex has to be larger than that for our cyano complex. Cool. All right, so that closes it out for this chapter here. Our discussion of color of these transition metal complexes. All right, we talked about why we have color in the first place, right? The absorbing of photons, exciting these electrons. We see that in our transition metal complexes because our d orbitals have split into these two energy levels, and we learned how we could calculate the difference in energy using the energy of those photons. All right, we also talked about this color wheel here, how we can predict what color we would observe depending on what's being absorbed by our sample. And then lastly, if we swapped out our ligands, we can apply our spectrochemical series here to predict the color of those complexes. Break. All right, cool. That's all I got for y'all. We're going to call it there. If